Everyone, this is Dr. Webb. So in this video we are starting our last big topic for the course, and that is the calculus of vector fields. And so this topic we're going to be pulling together all sorts of different things that we've done over this course. Vectors, curves, partial derivatives, integration. It's all going to come together in one place. So let's first talk about what a vector field is. Okay, so a vector field, and so we're going to be focusing on two-dimensional vector fields, but you can do 3 or 4-dimensional vector fields, or however many dimensions you want. The analogs to this are exactly what you'd expect them to be. But so for a vector field on R2, it's a function that takes every point on the xy plane and assigns it a vector from R2. Right, so it takes in 2 variables and it spits out a 2-dimensional vector. Right, so well, let's jump right into an example. So let's consider the vector field that takes x and y and spits out the vector where the x component is x plus y and the y component is x minus y. And so let's start plotting this. Right, so if we start at 0, well, 0 would just give us the 0 vector. Right. If we take the point 1, 0, well, 1 plus 0 is 1, 1 minus 0 is 1, and so at 1, 0, we're going to get the vector 1, 1. Right. If we plug in 1, 1, if we take the point 1, 1, well, 1 plus 1 is going to give me 2, 1 minus 1 is going to give me 0, and so this is going to be the vector 1 plus 1 is 2, 0. If I say take the vector 0, 1, 0 plus 1 is 1, and then 0 minus 1 is minus 1, so this is going to be the vector 1 minus 1, so that would give me that vector right here. So you can see that actually plotting this is rather slow, and so let's automate this. So right here you can see the vectors that we did before. The vector 1, 1 gave me 2, vector at 1, 0 it gave me 1, 1, at 0, 1 gave me 1 minus 1, and then it also did some additional vectors up here. As you can see, let's put in a little bit more. So this is going pretty much all the vectors that are x and y values are between 2 and -2 in whole values. And so you can kind of see how these vectors are shaping out. Let's go from -3 to +3. So you can see this is starting to get a jumble, but you can kind of see it looks like they're kind of converging in towards this line, kind of pointing towards this line going out this way, sort of. Go to 4, -4. Yeah, we can see it's getting even more, but it's getting a bit harder to see this, and it's partially because they're all sort of falling on top of each other. So one thing that we do is instead of drawing the full length, we might just put a different color in based on how long they are. So for this last one, the brighter the color, so the more towards red the color, the longer the vector actually is. But the actual vectors on here, they've all been normalized, so they're all exactly 1 long. So you can see how things are, as we get farther and farther away from the origin, the vectors tend to get longer and longer. Okay, so where are some places where vector fields pop up? So first, some real practical examples. Whenever you're talking about fluid flow, if you're talking about, you have some river, and you can talk about at some point in that river, what's the velocity vector for that water. And so these velocity vectors, over time, these tend to stay fairly constant. And so you can define a vector field that gives the velocity for water at each point inside the river. Another real common place you see vector fields are when they're used to represent forces, and so these are literally force fields, and so they can be used to represent electromagnetism, so either electricity or magnetism. They can be used to do gravity, so you've seen these before. If you think about, you take some magnet and north on one side, south on one side, you can actually make these practically. You take the iron fillings, and the iron fillings kind of come out and build in around the magnet. This is literally a physical type of force field. And so you can, and then what each point does is it's giving you the vector representing the pull of the force going in. So it takes each point, and the vector it spits out is the force applied there. And then a mathematical example that we've actually played around with a bunch of this term has been gradients, right? So if you have some function, let's see, we're going to use f again, so let's call it capital phi of xy. Well then, you can take the gradient of phi, and so remember this is a partial of phi in terms of x, partial of phi in terms of y. This is a vector field. And in fact, the gradients are a really important example of vector field. And so we're going to say that a vector field f is called conservative if it is the gradient for some function. Right? So if our vector field, we can find some function phi such that f is the gradient of phi, then that's going to mean that f is conservative. If you're familiar with the idea of conservative forces from physics, this is completely analysis. So a conservative force has a conservative vector field. In this setting, the function phi, such that when we take the gradient of phi, we get f, that is what's called the potential function of f. And potential there is sort of related to the idea of potential energy for a conservative force. So if we go back to the example that we had before for our vector field x plus y, x minus y, you can check that this is a conservative vector field because if I take the function x squared over 2 plus xy minus y squared, this is going to give me f. So let's just double check this. So here's our phi. If I take phi, do the partial in terms of x, I'm going to get 2x over 2, which is just x, plus the derivative of xy in terms of x is just y, and then minus y squared, that's going to go to 0. The partial in terms of y of this, x squared over 2 is going to go to 0, plus xy, derivative in terms of y is going to be x, minus y squared over 2, take the derivative, going to get 2y over 2, which is y. And so there are our two partials, and you can see these two partials match up with the component functions for f. Okay, so how can you actually tell that a vector field is conservative, right? And so remember, if it's conservative, then that means that there exists some function phi where if I take the partial of phi in terms of x, I'm going to get that component, and if I take the partial of phi in terms of y, I'm going to get that component. So how can we tell, looking at these two, that there's some overlying phi coming out of this, right? And so one way to do this is to try and maybe integrate it in some way, but that's often kind of annoying. Integration is often an annoying thing. Is there another way to do this? And the answer is yes, there is. And it's using the fact that, if you recall from when we did partial derivatives, if I do the partial in terms of x and then do the partial in terms of y, that's the same thing as starting off doing the partial in terms of y and then doing the partial in terms of x, right? So if I take my x component function, so in this case it's f of xy, that's supposed to be the partial derivative in terms of x. If I then take its partial in terms of y, so f sub y, well then that should match what happens when I take my y component function, and so that should be what we get after we take the partial in terms of y, and then take the partial of that in terms of x. Okay, and so that is the test. So you take the x component function, the f here, you take the partial in terms of y, you take the g component function, partial of g over, and then you take its partial in terms of x, right? So if we go back and think about the vector function, the vector field we've been looking at, x plus y, x minus y, well, so this is my f, this is my g, my partial of f in terms of y is 1, my partial of g in terms of x is also 1, and so these two match up, and so this works. Yeah, so this is actually a much quicker way to show that something's conservative, rather than trying to integrate up and trying to figure out actually what the potential function is, right? And so this is useful if you're trying to figure out if something is conservative, because if you're not sure, integrating can take a long time to do. And so if you're not sure and then you integrate it, and it's kind of hard to tell, because you're integrating two different functions, it's a little bit difficult to see if things match up the way that you want them to sometimes. And so the only way, so it's much easier to actually do this test where you're essentially checking that the mixed partials would work. And then if that works, then that tells you you have to be able to find the potential function. And so often that makes things a little less frustrating. Okay, so let's close this off with an example where we're going to talk about, first we're going to show that this is conservative, and then we're going to talk about, once we know that it's conservative, how do we actually find the potential function. So first, let's show this is conservative. So there's my f, there's my g. So if I take my f, take the partial in terms of y, so derivative of sine y is going to be cosine y, plus 2x goes away, plus 4y gives me 4. My partial of g in terms of x is derivative of x cosine y, the x goes away, I'm left with cosine y, minus 3y squared goes away, and then the plus 4x, take the derivative in terms of x, is going to give me 4. So both of these, gives me cosine of y plus 4, cosine of y plus 4, these match, and so we know this is conservative. Okay, So this passed the conservative field test. Okay, so now that we know that it's conservative, now let's find the potential function. Okay, and so to find the potential function, so remember that f here, this is the partial of whatever phi is in terms of x, and g is the partial of whatever phi is in terms of y. Okay, and so if we integrate f in terms of x, we're going to get back lots of phi, but we're going to remember that when whatever phi looks like, if there was some part of it that only involved y, when we took the partial in terms of x, that would have disappeared. Okay, but let's start by integrating our f of xy in terms of x. Okay, and so all of the y's we're going to keep as constants, and so this is integral sine y plus 2x plus 4y in terms of x. So sine y is a constant, integrating in terms of x is going to give me x sine y plus 2x. When I integrate it, I'm going to get x squared, and then plus 4y. When I integrate it, I'm going to get 4xy. And so then, since this is like an indefinite integral, I need to add a plus c, but this plus c here, it actually could contain y's. And so I'm going to put c being a function of y. It could be constants or things just involving y, because when you take the derivative of this whole thing, take the partial in terms of x, this cy is the part that would go to 0. Everything that's left here would spit this back out. Okay. So now we're going to go back and we're going to do the same thing with g, except we're going to be integrating g in terms of y. And so g in terms of y is going to be x cosine y minus 3y squared plus 4x dy. So when we integrate this in terms of y, x is a constant. The integral of cosine y is sine y. Minus 3y squared becomes y cubed. Plus integral of 4x in terms of y is going to be 4xy. And then at the end of this, I'd have a constant. But for the same reason I have a constant in terms of y, for the first one, I'm going to have another constant. Let's call it c1. And this is going to be a function just of x. Okay, so now we've integrated both of them, and let's compare the two. Okay, so comparing the two, we notice that they both have x sine y, and they both have 4xy. Now, my top one, the integral of f in terms of x, it has an x squared. That's a function that just involves x. And so that's going to correspond to that c1x. My bottom function, it has a minus y cubed. That's a function that just involves y. So that's going to be my function c of y. Okay? And so when we put this together, our phi function here, well, it's going to have, notice that the two functions that it shares both have x's and y's in them. So phi of xy is going to have x sine y plus 4xy. And then I'm going to add in the x squared and subtract off the minus y cubed. Okay, and so if you look, I've got sine xy and 4xy. These appeared in both of these integrals, both of these antiderivatives. The x squared came from f, and that's covering the c1 of x. The minus y cubed came from the integral of g in terms of y, and that's going to cover my c of y. Okay? And so this is going to work for our phi. And just to double check, let's make sure. So if that's my phi, what happens when I take the partial of phi in terms of x? Well, x sine y is going to turn into sine y, plus 4xy turns into 4y, and then plus x squared gives me 2x. That matches f. If we take the partial of phi in terms of y, so I'm taking derivative of x cosine y in terms of y, so the x is a constant, cosine y turns into x sine y, excuse me. I'm taking the derivative of x sine y, so x stays the same, sine y becomes cosine y, plus derivative of 4xy in terms of y is going to give me 4x, plus x squared in terms of y is going to be 0, and then minus y cubed is going to give me 3y squared. And so x cosine y plus 4x minus 3y squared, that matches our y component function for f. So this phi does work as our potential function. So do say its potential function. We should say find a potential function for it, because at this point I could get any other potential function here by adding some constant, let's call it k since we already used c a bunch. That's just a real number, and so in either case taking the derivatives of that would make it go to 0. Okay, that is all that I have for you for this video. I will see you again soon.